So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're lying on a planet that's spinning at about 1,000 miles an hour at the equator. And that planet is hurtling around a star at roughly 67,000 miles an hour. And that star, our sun, is sweeping through the Milky Way galaxy at something like 450,000 miles an hour. And the galaxy itself is drifting through the universe at a speed that, honestly, depends on what you measure it against. But it's fast, incomprehensibly fast, and you feel none of it. Not a whisper. You feel still. You feel like you're just lying there, breathing, maybe a little tired, maybe letting your thoughts slow down. And that gap between what's actually happening and what you feel, that's kind of where astrophysics lives. It's the science of figuring out what's really going on out there, even when our senses tell us something completely different. And the beautiful thing is, people have been staring up at the sky and trying to work this out for thousands of years. Long before anyone had a telescope, long before anyone knew what a star actually was, people looked up and noticed patterns. They noticed that the sun rose and set in a predictable way. They noticed that certain bright points of light moved against the background of other bright points. They noticed that the moon changed shape on a cycle, and they started counting those cycles. And that's how we got months. The word month literally comes from moon. So in a very real sense, the first piece of astrophysics anyone ever did was just paying attention, watching the sky night after night and asking, why does it do that? Now, the ancient Greeks get a lot of credit here, and they deserve a good chunk of it. But they weren't the only ones. The Babylonians, working in what's now Iraq, were keeping meticulous records of planetary positions as far back as maybe 1800 BCE. They had clay tablets, actual clay tablets that archaeologists have dug up, covered in cuneiform script, tracking the movements of Venus, Mars, Jupiter. They weren't doing it for the reasons we'd think of as scientific, not exactly. A lot of it was tied to omens and divination, trying to read the will of the gods in the movements of the planets. But here's the thing. To do that, they had to be incredibly precise observers. They had to develop mathematical systems for predicting where a planet would be months or years in the future. And they got good at it. Remarkably good. They developed what we'd now call arithmetic methods for modeling planetary motion, using sequences and interpolation, and some of their predictions were accurate to within a few degrees. That's not nothing. That's real mathematical astronomy, even if the motivation was astrology. The Greeks took things in a slightly different direction, and this is where the story gets really interesting from a physics standpoint. See, the Babylonians were great at prediction. They could tell you where Jupiter would be next spring, but they weren't necessarily asking why. The Greeks, or at least some of them, started asking why. What's the actual structure of the cosmos? What are things made of? How are they arranged? And the model they came up with, the one that stuck around for an almost unbelievable amount of time, was the geocentric model. Earth at the center, everything else revolving around it. Now, before you roll your eyes at that, think about it from their perspective. Stand outside on a clear night and just watch. The stars appear to rotate around you in a great dome. The sun rises, crosses the sky, and sets. The moon does the same. It genuinely looks like everything is going around you. The geocentric model isn't stupid. It's intuitive. It matches what you see. The hard part, the really hard part, was going to be proving that it was wrong. The person who formalized the geocentric model into its most sophisticated form was Claudius Ptolemy, working in Alexandria around 150 CE. And Ptolemy was brilliant, genuinely brilliant. His book, The Almagest, is one of the most influential scientific texts ever written. What Ptolemy did was take centuries of observational data and build a geometric model that could predict planetary positions with impressive accuracy. But to make it work, he had to introduce some pretty clever, some might say tortured, mechanisms. The big one was epicycles. Here's the idea. If a planet just moved in a simple circle around the Earth, its motion would be smooth and steady. But planets don't do that. Mars, for instance, does this weird thing where it appears to slow down, stop, move backward for a few weeks, stop again, and then resume its forward motion. It's called retrograde motion, and it's one of the most confusing things you can observe if you think Earth is sitting still at the center of everything. So Ptolemy's solution was to say, okay, the planet moves in a small circle, an epicycle, and the center of that small circle moves along a larger circle, the deferent, around the Earth. If you tune the sizes and speeds just right, you can reproduce that backward looping motion. It's like if you taped a pen to the rim of a small wheel and then rolled that small wheel around the rim of a bigger wheel. The pen would trace out these loopy, petal-shaped curves. And that's essentially what Ptolemy proposed the planets were doing. It's geometrically elegant in its own way, and it worked. It predicted planetary positions well enough to be useful for over 1,000 years. Think about that. 14 centuries. That's how long Ptolemy's model dominated Western and Islamic astronomy. Not because people were foolish, but because it was genuinely good at its job. But here's the thing that nagged at people, even back then. The system kept getting more complicated. Every time observations got a little more precise, you needed to add another epicycle, or tweak an existing one, or introduce a new geometric device called an equant, which even Ptolemy's admirers found a bit ugly. The equant was this point, offset from the center of the deferent, from which the planet's angular motion appeared uniform. It worked mathematically, but it violated the Greek philosophical ideal that celestial motion should be based on perfect, uniform circular motion. It was a kludge. A brilliant kludge, but a kludge. And there were people, even in antiquity, who suspected the whole framework might be wrong. Aristarchus of Samos, back around 270 BCE, so centuries before Ptolemy, proposed a heliocentric model. Sun at the center, Earth going around it. He even tried to estimate the relative distances to the Sun and Moon using geometry during a lunar eclipse, and while his numbers were way off, his method was sound. But his heliocentric idea didn't catch on. Partly because it contradicted common sense, you don't feel the Earth moving. Partly because it raised a technical objection that nobody could answer at the time. If the Earth is moving around the Sun, you should see the nearby stars shift position against the more distant ones as your vantage point changes. That's called stellar parallax. And it's a real effect, but the stars are so incredibly far away that the shift is tiny. Way too tiny for ancient observers to detect. So the absence of observable parallax was actually used as evidence against the heliocentric model. It was a perfectly reasonable argument based on the available data. It just happened to be wrong. So the geocentric model reigned. Through the fall of Rome, through the preservation and elaboration of Greek knowledge in the Islamic world, where astronomers like al-Battani and al-Tusi made significant refinements and corrections, through the medieval European period where Ptolemy's Almagest was rediscovered and translated from Arabic into Latin. For all those centuries, the basic picture was the same. Earth at the center, celestial spheres carrying the planets, the stars fixed on an outermost sphere. It was tidy. It was sanctioned by the Church. It matched everyday experience. And it was, at its core, wrong. The person who finally, publicly, and mathematically challenged it was Nicholas Copernicus, a Polish canon, that's a church official, who spent decades quietly working on an alternative. Copernicus published his major work, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, in 1543, the year he died. And there's a story, possibly apocryphal, but too good not to mention, that a copy of the printed book was placed in his hands on his deathbed. Whether that's literally true or not, the timing is real. He held off publishing for years, likely because he feared ridicule or controversy or both. Now here's what's important to understand about Copernicus. His model was heliocentric, sun at the center, Earth as a planet orbiting it, but it wasn't a clean break from the old system. He still used circles. He still needed epicycles, though fewer of them. His predictions weren't dramatically better than Ptolemy's, at least not at first. What his model had going for it was elegance of explanation. Retrograde motion? You didn't need epicycles to explain the basic phenomenon anymore. Mars appears to go backward simply because Earth, on a faster inner orbit, overtakes it. It's like passing a slower car on the highway. As you go by, the other car appears to drift backward against the distant landscape. That's it. That's the whole explanation. No epicycles needed for that particular puzzle. And that simplicity was deeply appealing, at least to some people. But not to everyone, and not right away. The Copernican model had real problems. If the Earth was spinning on its axis, why didn't we feel it? Why didn't objects fly off the surface? If the Earth was moving through space, why didn't we observe stellar parallax? These weren't trivial objections. They were good physics questions that wouldn't be fully answered for another century or more. And the theological implications were enormous. Removing Earth from the center of creation wasn't just a geometric rearrangement. It was a philosophical earthquake. If Earth is just another planet, what does that say about humanity's special place in the cosmos? These questions would eventually entangle astronomers with the Church in ways that got genuinely dangerous. But before that confrontation reached its peak, something happened that changed everything. And it started with a man who had a golden nose. Tycho Brahe, born in 1546 in what's now Sweden, was one of the most extraordinary characters in the history of science. He was a Danish nobleman, flamboyant, argumentative, and obsessed with precision. He lost part of his nose in a duel, reportedly over a mathematical dispute, which tells you something about the man, and wore a prosthetic made of metal, possibly brass or copper, though legend says gold. He kept a pet moose that reportedly died after drinking too much beer and falling down a flight of stairs. I'm not making this up. Tycho Brahe's life reads like a novel. But here's why he matters for astrophysics. He was the greatest naked-eye astronomical observer who ever lived. Before telescopes existed, Tycho built enormous instruments, quadrants, sextants, armillary spheres, on his private island observatory called Uraniborg, funded by the King of Denmark. And with these instruments, he measured the positions of stars and planets to an accuracy of about 1 arc-minute. That's 1/60th of a degree. For comparison, the best observations before Tycho were accurate to maybe 10 or 15 arc-minutes. He improved precision by an order of magnitude, and he did it through sheer engineering ingenuity and obsessive attention to detail, calibrating his instruments, accounting for atmospheric refraction, checking and rechecking every measurement. And Tycho's data would turn out to be the key that unlocked the actual shape of planetary orbits. But Tycho himself didn't do that unlocking. He had his own model of the solar system, a compromise where the planets orbited the sun but the sun orbited the Earth. And he guarded his data jealously. The person who would finally crack the code was his assistant, a young German mathematician named Johannes Kepler, and the relationship between these two men was complicated, tense, and ultimately tragic. Kepler arrived in Prague in the year 1600, invited by Tycho, who had recently relocated there after falling out of favor with the new Danish king. And from the very beginning, there was friction. Tycho recognized Kepler's brilliance. The young man had already published a bold cosmological work called the Mysterium Cosmographicum, in which he tried to explain the spacing of the planets using nested geometric solids. It was wrong, beautifully wrong, but it showed a mind that thought in sweeping, ambitious terms. Tycho needed someone like that to help make sense of his decades of observations. But Tycho was also deeply protective. He parceled out data to Kepler in small, controlled doses, never giving him the full picture. He assigned Kepler the problem of Mars, the planet whose motion was the most troublesome, the most irregular, the one that had resisted every attempt at a clean geometric explanation. Maybe Tycho thought it would keep Kepler busy and frustrated. Maybe he genuinely believed Kepler was the one who could crack it. Either way, it was like handing someone the hardest puzzle in the box and saying, "Here, work on this." And then, in October of 1601, Tycho Brahe died. The circumstances were strange. He fell ill after a banquet in Prague, suffered from a bladder ailment, and died 11 days later at the age of 54. For centuries there were rumors of poisoning, possibly by Kepler himself, and when Tycho's body was exhumed in 2010, researchers actually tested his remains for mercury. The results were inconclusive but leaned toward natural causes, probably a severe urinary infection that went septic. But the drama of it all, the timing, is remarkable. Because with Tycho gone, Kepler moved quickly to secure access to the full dataset. There were legal battles with Tycho's heirs, arguments about who owned the observations, but Kepler eventually got what he needed. And then he sat down, with the most precise astronomical measurements in human history, and the most stubborn planet in the sky, and he went to work. What followed was nearly 6 years of grueling calculation, and I want you to appreciate what that means, because Kepler didn't have a calculator, he didn't have a computer, he didn't even have logarithms yet. Those wouldn't be published by John Napier until 1614. Every calculation was done by hand, long division and multiplication of numbers with many decimal places, page after page of arithmetic. Kepler later described his work on Mars as his war with the planet, and he wasn't being dramatic. He tried everything. He tried circles. He tried circles with the sun slightly off-center, which is called an eccentric. He tried circles with an equant point, the old Ptolemaic trick. And he got close. At one point, his model matched Tycho's observations to within about 8 arc minutes. 8 arc minutes. That's a tiny sliver of sky. Most astronomers would have called that good enough and moved on. But here's the thing about Kepler, and this is what makes him one of the most important figures in the history of science. He refused to accept 8 arc minutes of error, because he knew Tycho's data was accurate to about 2 arc minutes. If the model was off by 8, the model was wrong. Not approximately wrong. Wrong. And Kepler had enough intellectual honesty, enough stubbornness, enough faith in the quality of Tycho's observations to throw out years of his own work and start over. Think about what that takes. Think about the discipline required to look at a result that's 99% right and say, no, I need to find the answer that's actually right. That moment, that decision, is one of the most consequential in the history of physics. because it forced Kepler to abandon the circle. And abandoning the circle was an enormous conceptual leap. For 2,000 years, from Plato through Ptolemy through Copernicus, everyone had assumed that celestial motion must be circular. Circles were perfect. The heavens were perfect. Therefore, heavenly bodies moved in circles. It was so deeply embedded in the culture of astronomy that questioning it felt almost heretical. But Kepler's 8 arc minutes wouldn't go away, and so he tried something radical. He tried an oval, then he tried an egg shape, and finally, after enormous labor, he landed on the ellipse, a stretched circle, a shape defined by 2 focal points rather than one center. And when he placed the Sun at one focus of an elliptical orbit and calculated Mars's path, the numbers matched. Not approximately, not within 8 arc minutes. They matched Tycho's data almost perfectly. This became Kepler's first law of planetary motion, published in 1609 in his book Astronomia Nova. Planets move in ellipses with the Sun at one focus, and his second law came from the same work. The idea that a line connecting a planet to the Sun sweeps out equal areas in equal times. What that means, practically, is that a planet moves faster when it's closer to the Sun and slower when it's farther away. If you imagine drawing a triangle from the Sun to the planet at 2 different points in its orbit, separated by, say, 30 days, the area of that triangle is always the same, whether the planet is close in and zipping along or far out and drifting slowly. It's a beautiful, elegant relationship, and it fell directly out of the data. Now, Kepler's third law came later, in 1619, in a work called Harmonices Mundi, the harmony of the world. And this one connects the size of a planet's orbit to how long it takes to complete one trip around the Sun. Specifically, the square of the orbital period is proportional to the cube of the semi-major axis, the semi-major axis being half the longest diameter of the ellipse. So if you know how far a planet is from the Sun, you can calculate how long its year is, and vice versa. Mercury, close in, whips around in about 88 Earth days. Saturn, way out there, takes over 29 Earth years. And they all obey this same mathematical relationship, every single one. Here's what's remarkable about Kepler's laws, though. He discovered them empirically. He found the patterns in the data, but he couldn't explain why. Why ellipses? Why equal areas? Why that particular relationship between distance and period? Kepler himself speculated about some kind of force emanating from the Sun that pushed the planets along, something like magnetism maybe, but he never nailed it down. The why would have to wait another several decades for a man born in England on Christmas Day, 1642, or January 4th, 1643, depending on which calendar you use, in a small manor house in Lincolnshire. A premature baby so tiny his mother said he could have fit inside a quart mug. Isaac Newton. And Newton's story is one of those that almost feels too dramatic to be real. His father died before he was born. His mother remarried when he was 3 and left him with his grandmother. He grew up angry, isolated, brilliant. At Cambridge, he was an unremarkable student until the Great Plague of 1665 forced the university to close, and Newton retreated to his family's farm in Woolsthorpe. And there, over the course of roughly 18 months, his so-called annus mirabilis, though it was actually closer to 2 years, he essentially invented calculus, developed his theory of color and optics, and began formulating the law of universal gravitation. He was 23 years old. It's one of the most extraordinary bursts of intellectual productivity in human history, and it happened because a plague shut down his school and left him alone with his thoughts. Now, the apple story. You've heard it. Did an apple really fall on Newton's head and inspire his theory of gravity? almost certainly not on his head. But Newton himself, late in life, told the story to multiple people. His friend William Stuckley recorded a version of it, and so did Voltaire, who heard it from Newton's niece. Newton said he was sitting in the garden at Woolsthorpe, saw an apple fall, and began to wonder, does the same force that pulls the apple to the ground also reach up to the moon? Does it extend that far? And if so, does it get weaker with distance? And if it does, by how much? That question, does the force that makes things fall also govern the motion of the moon, is deceptively simple. But answering it required Newton to do something no one had ever done before. He had to show that the same mathematical law could explain both the trajectory of a falling apple and the orbit of the moon around the Earth. And to do that, he needed to figure out exactly how gravity weakens with distance. His insight, which he worked out using geometry and his newly invented calculus, was that gravitational force follows an inverse square law. Double the distance, and the force drops to 1/4. Triple the distance, it drops to 1/9. The force between two objects is proportional to the product of their masses divided by the square of the distance between them. That's it. That's the law of universal gravitation, and the word universal is doing a lot of work there, because Newton was claiming that this law applies everywhere, not just on Earth, not just in the solar system, but throughout the entire cosmos. The same force that pulls your blanket toward the mattress right now is the force that keeps galaxies from flying apart. And here's where it connects back to Kepler, because Newton was able to show mathematically that if gravity follows an inverse square law, then Kepler's 3 laws of planetary motion follow as necessary consequences. Elliptical orbits, equal areas in equal times, the relationship between period and distance, all of it drops out of Newton's gravitational equation combined with his laws of motion. Kepler found the patterns. Newton found the reason. And that's a distinction worth sitting with for a moment, because it represents a fundamental shift in how we understand the universe. Before Newton, astronomy was mostly about describing, cataloging positions, tracking motions, fitting curves to data. After Newton, it became about explaining. You could ask why, and you could get an answer that was mathematical, testable, and universal. Newton published all of this in 1687 in the Principia Mathematica, a book that is routinely described as the most important scientific work ever written. And honestly, it's hard to argue with that. The Principia didn't just give us gravity. It gave us the 3 laws of motion. Every object stays at rest or in uniform motion unless acted on by a force. Force equals mass times acceleration. Every action has an equal and opposite reaction. These are the foundation of classical mechanics, the framework that would dominate physics for over 2 centuries, and that still works beautifully for almost everything you encounter in daily life. When engineers design bridges, when NASA plots trajectories to Mars, when you calculate how far a ball will fly if you throw it at a certain angle, that's all Newton. Still, after more than 300 years. But Newton's gravity, for all its power, had a problem. Actually, it had several, but one in particular that would gnaw at physicists for centuries. Newton's law described what gravity did. It told you exactly how strongly 2 masses attract each other and how that attraction shapes their motion. But it said nothing about how gravity actually works. How does the Earth know the sun is there? How does the gravitational influence travel across 93 million miles of empty space? Newton himself was deeply uncomfortable with this. In a famous letter, he wrote that the idea of one body acting on another through a vacuum, with nothing mediating the interaction, was so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. He knew his theory was incomplete. He just couldn't see what was missing, and for a long time, nobody could. Newtonian gravity worked so well, predicted so accurately, that most physicists simply accepted the mystery and moved on. The theory predicted the existence of the planet Neptune before anyone had ever seen it. In 1846, the French mathematician Urbain Le Verrier noticed that Uranus wasn't quite following the path Newton's equations predicted, and he calculated that another planet must be tugging on it from farther out. He told astronomers where to point their telescopes, and there was Neptune, within 1 degree of where he said it would be. That's an astonishing triumph. When your theory can predict the existence of an unseen planet based purely on mathematics, you tend to trust it pretty deeply. But there was one orbit that Newton's gravity couldn't quite explain, and it involved the planet closest to the Sun, Mercury. Mercury's orbit has a slight peculiarity. The point of its closest approach to the Sun, called the perihelion, shifts a tiny bit with each orbit. The ellipse slowly rotates. Most of this precession is caused by the gravitational pull of the other planets, and Newtonian mechanics accounts for almost all of it. But there's a leftover, about 43 arc-seconds per century, that Newton's theory simply cannot explain. Leverrier noticed this too, and he tried the same trick that had worked with Neptune. He proposed a hidden planet, even closer to the Sun than Mercury, which he called Vulcan. Astronomers searched for decades. Some even claimed to have spotted it. But Vulcan didn't exist. The answer to Mercury's anomalous precession would come from an entirely different direction, from a patent clerk in Bern, Switzerland, who in 1905 was about to start dismantling everything Newton had built, not by proving it wrong exactly, but by showing that it was incomplete. A special case of something deeper, something stranger, something that would bend the very fabric of space and time into shapes no one had ever imagined. And here's what's fascinating about Einstein. He didn't start with Mercury. He wasn't trying to fix that 43 arc-second problem. He was thinking about something far more fundamental, something that had been bothering him since he was a teenager. He was thinking about light. Picture a 16-year-old Albert Einstein growing up in Munich, daydreaming. And this is a daydream he later described himself, about what it would be like to ride alongside a beam of light. If you could somehow travel at the speed of light, what would a light wave look like to you? Would it appear frozen, like a standing wave, just hanging there in space? That image troubled him, because nothing in Maxwell's equations, those beautiful equations describing electromagnetism, allowed for a stationary light wave. Light, by its very nature, had to move. It couldn't just sit still. So something about the picture didn't work. Either you couldn't actually catch up to light, or the physics of light was stranger than anyone realized. That question sat in the back of his mind for nearly a decade, and in 1905, working as a third-class patent examiner in Bern, because no university would hire him, he'd annoyed too many professors, Einstein published a paper that answered it. The paper was called On the Electrodynamics of Moving Bodies, and it contained what we now call special relativity. The core idea is deceptively simple, and it's worth taking a moment to really sit with it. Einstein proposed two things. First, the laws of physics are the same for everyone moving at a constant speed. There's no experiment you can do inside a sealed room that will tell you whether you're moving or standing still, as long as you're not accelerating. That part isn't even controversial. Galileo had said something similar centuries earlier, but the second part is where everything goes sideways. Einstein said that the speed of light in a vacuum is the same for all observers, no matter how fast they're moving relative to the light source. Not just approximately the same, exactly the same. Always. About 299,792 kilometers per second, whether you're standing still or hurtling toward the light at half its speed. Now think about what that means. In everyday life, speeds add up. If you're on a train going 60 miles an hour and you throw a ball forward at 20 miles an hour, someone standing on the platform sees the ball going 80. Simple addition. But Einstein is telling you that light doesn't work this way. If you're on a spaceship going half the speed of light and you turn on a flashlight, you see the light leave at the speed of light, and someone standing still, watching your ship zoom past, also sees that same light moving at the speed of light, not 1.5 times the speed of light, as simple addition would suggest, the same speed. For both of you, that seems impossible, right? How can both observers measure the same speed for the same beam of light when they're moving relative to each other? Something has to give. And what gives, here's the thing that makes your brain itch the first time you hear it, is space and time themselves. For the math to work, for both observers to honestly measure the same speed of light, time has to pass at different rates for people moving at different speeds, and distances have to contract. A clock on a fast-moving spaceship ticks slower than a clock sitting on your nightstand, not because the clock is broken, not because of some mechanical effect. Time itself, the actual passage of moments, slows down for the moving clock, and the spaceship itself gets physically shorter in the direction it's traveling, as measured by a stationary observer. This is called time dilation and length contraction, and I know it sounds like science fiction, but it's been measured. It's been confirmed thousands of times with extraordinary precision. We see it in particle accelerators, where subatomic particles called muons, which have a known, very short lifespan, survive far longer than they should when they're moving at close to the speed of light. They live longer because time is literally passing more slowly for them. We see it in GPS satellites, which carry atomic clocks that tick at a slightly different rate than clocks on the ground. And the GPS system has to correct for this relativistic effect. If it didn't, your phone's map would drift by about 10 kilometers per day. So this isn't abstract philosophy. It's engineering. It's in your pocket right now. But special relativity, as revolutionary as it was, had a limitation. It only dealt with objects moving at constant speeds. No acceleration, no gravity. And Einstein knew that wasn't enough. Gravity was the big one. Newton had described gravity as a force that acts instantly across empty space, a kind of invisible rope pulling masses toward each other. But Einstein found that idea deeply unsatisfying. How does the Earth know the sun is there? How does the gravitational influence travel? Newton himself had admitted he had no answer to this. He famously wrote, "I frame no hypotheses about the mechanism of gravity." He just described what it did, not how it worked. Einstein spent the next 10 years, from 1905 to 1915, wrestling with this problem, and those 10 years nearly broke him. This wasn't a flash of insight like special relativity. This was a grinding, exhausting intellectual battle. He had to teach himself entirely new branches of mathematics, tensor calculus, Riemannian geometry, mathematical tools that describe curved surfaces and spaces. He made wrong turns. He published equations in 1913 that he later realized were incorrect. He collaborated with his friend Marcel Grossmann, who helped him with the math. He separated from his first wife, Mileva. His health suffered, and the whole time he was in a quiet race with David Hilbert, one of the greatest mathematicians alive, who was working on the same problem from a purely mathematical direction. In November 1915, Einstein presented his field equations of general relativity to the Prussian Academy of Sciences, and they are, I don't think this is an exaggeration, among the most beautiful and profound equations in the history of human thought. What they say, at their core, is this: gravity is not a force. Gravity is geometry. Mass and energy don't pull on other objects through some mysterious invisible rope. Instead, mass and energy curve the fabric of space-time itself, and objects moving through that curved space-time follow the straightest possible paths, which, in curved space, aren't straight at all. They're curves, orbits. Let me try to make that more concrete, because it's one of those ideas that sounds poetic, but can feel slippery if you don't pin it down. Imagine a stretched rubber sheet, the classic analogy, and it's imperfect, but it helps. If you place a heavy bowling ball in the center, the sheet sags, creating a dip, a curve in the surface. Now roll a marble across the sheet. If you roll it in a straight line far from the bowling ball, it barely curves. But if you roll it closer, it follows the curve of the dip. It bends toward the bowling ball. It might even spiral around it. Not because the bowling ball is pulling on the marble with some invisible thread, but because the marble is following the shape of the surface, it's moving on. The surface itself is curved, and the marble is just going where the geometry tells it to go. That's what planets are doing around the sun. The sun's mass warps the space-time around it, and Earth follows the curved path through that warped space-time. It feels like a force. We experience it as gravity. But in Einstein's picture, it's really just geometry. The Earth is moving in the straightest line it can through curved space. And here's what's really clever. This framework doesn't just reproduce everything Newton got right. It fixes the things Newton got wrong. Remember Mercury? That stubborn 43 arc-seconds per century of unexplained precession? Einstein's equations predicted exactly. When he first calculated Mercury's perihelion precession using general relativity and got the right answer, he later said his heart physically palpitated. He was so excited he couldn't work for days. After 10 years of struggle, the universe had told him he was on the right track. But a theory needs more than explaining old puzzles. It needs to predict new things. And general relativity made a dramatic prediction that could be tested. It said that light itself should bend when it passes near a massive object, because the light is following the curvature of space-time. The sun should deflect starlight passing close to it, and Einstein calculated exactly how much, about 1.75 arcseconds for light grazing the sun's edge. That's a tiny angle, but it was measurable, and crucially, it was twice the value that a simple Newtonian calculation would give. So this was a clean test. Newton says one number, Einstein says another, and you can check. The problem is that you can't normally see stars near the sun because, well, the sun is blindingly bright. You need a total solar eclipse. And so, in 1919, the British astronomer Arthur Eddington organized 2 expeditions. One to the island of Principe off the west coast of Africa, and one to Sobral in northern Brazil, to photograph stars near the sun during the eclipse of May 29th. The conditions weren't ideal. Principe was cloudy for much of the eclipse, and Eddington only got a few usable plates. But when the measurements were analyzed, they matched Einstein's prediction, not Newton's. The announcement came on November 6, 1919, at a joint meeting of the Royal Society and the Royal Astronomical Society in London. The room was packed. J.J. Thomson, the president of the Royal Society, declared it one of the greatest achievements in human thought. The next morning, the Times of London ran the headline, "Revolution in Science, New Theory of the Universe, Newtonian Ideas Overthrown." Einstein became the most famous scientist in the world overnight. And the thing is, the 1919 measurements were actually not that precise. Later analyses have shown the error bars were large enough that the result was somewhat ambiguous. But subsequent eclipse observations, and eventually radio astronomy measurements that don't need eclipses at all, confirmed Einstein's prediction with extraordinary accuracy. He was right. So now we have this extraordinary new framework. Space-time is a dynamic thing. It curves, it bends, it responds to the matter and energy within it, and matter responds to the curvature. As the physicist John Wheeler later put it, in one of the most elegant summaries ever coined, space-time tells matter how to move. Matter tells space-time how to curve. That's general relativity in 12 words. But here's where it gets even more interesting, because Einstein's equations don't just describe gentle curves around stars and planets. They allow for extreme curvature, situations where space-time is bent so violently that something truly strange happens, where the curvature becomes so steep, so extreme, that nothing, not even light itself, can climb back out. And that idea, honestly, is one of the most disorienting things in all of physics. So let's sit with it for a while. The funny thing is, the concept of something so massive that light couldn't escape from it actually predates Einstein by more than a century. Back in 1783, an English clergyman and natural philosopher named John Michell, a man who deserves far more recognition than he gets, wrote a paper for the Philosophical Transactions of the Royal Society, in which he imagined a star so large and so dense that its escape velocity would exceed the speed of light. He called these hypothetical objects dark stars, and he reasoned, quite logically given Newtonian physics, that if light were made of particles, which was Newton's own view, then a sufficiently massive body would simply pull those particles back down before they could get away. You'd have a star that was, in effect, invisible. Pierre-Simon Laplace, the great French mathematician, independently arrived at a similar idea a few years later. But both of them were working within Newtonian gravity, and the concept didn't really go anywhere. It was a curiosity, a thought experiment. Nobody had the mathematical framework to take it further. Then Einstein's general relativity comes along in 1915, and almost immediately, within weeks, actually, a German physicist and astronomer named Karl Schwarzschild finds an exact solution to Einstein's field equations. And this is remarkable for a couple of reasons. First, because the field equations are incredibly complex. They're a set of 10 coupled, nonlinear partial differential equations, and Einstein himself didn't think exact solutions would come easily. He'd been working with approximations. But Schwarzschild, who was brilliant, found an exact solution for the simplest possible case, a perfectly spherical, non-rotating, uncharged mass sitting alone in empty space. Now here's the poignant part. Schwarzschild did this work while serving in the German army on the Eastern Front during World War I. He was stationed in Russia, calculating artillery trajectories by day and solving the deepest equations in theoretical physics by night. He sent his solution to Einstein in a letter, and Einstein presented it to the Prussian Academy of Sciences in January 1916. Schwarzschild died just a few months later, in May 1916, from a painful autoimmune disease he'd contracted at the front. He was 42 years old, but his solution lived on, and it contained something deeply unsettling. The Schwarzschild solution described how space-time curves around a spherical mass, and it worked beautifully for ordinary objects like stars and planets. It gave you the same predictions as Newton for weak gravitational fields, but with corrections that matched observations like Mercury's orbit. However, the math also showed that for any given mass, there was a critical radius, a specific distance from the center, at which something very strange happened. At that radius, certain terms in the equations blew up. They went to infinity, and inside that radius, the curvature of spacetime became so extreme that all paths, even the path of light, curved inward. Nothing could move outward past that boundary. Schwarzschild calculated this critical radius, and it's elegantly simple. It's 2 times the mass of the object, multiplied by Newton's gravitational constant, divided by the speed of light squared. For the Sun, that works out to about 3 kilometers. Meaning, if you could somehow compress the entire mass of the Sun into a sphere just 3 kilometers across, about the size of a small town, space-time would curve so severely that this boundary would form, and the Sun would become one of these objects. For decades, almost nobody believed this could actually happen in nature. Einstein himself was deeply skeptical. In 1939, he published a paper arguing that matter could not be compressed to the point where this Schwarzschild boundary, what we now call the event horizon, would form. He thought some physical process would always intervene to prevent it. And honestly, his intuition was understandable. The idea is genuinely bizarre. Think about what an event horizon means. It's not a physical surface. It's not a wall. If you were falling toward one, you wouldn't see a boundary or feel a barrier. You'd cross it without even noticing. At least, that's what the math says. But once you crossed it, you could never come back. Every direction you could move, including what you'd perceive as outward, would actually lead you deeper inward. The geometry of space-time itself would have rearranged so that the future, all possible futures, point toward the center. That's not a force pulling you in. That's the structure of space and time, funneling you in one direction, the way the structure of ordinary space-time funnels all of us toward the future. Inside an event horizon, falling inward is as inevitable as Tuesday following Monday. The term black hole didn't even exist until the 1960s. John Wheeler, the same Wheeler who gave us that beautiful summary of general relativity, is generally credited with popularizing the term, though there's some debate about whether he coined it or picked it up from an audience member at a conference in 1967. Before that, physicists used clunky terms like gravitationally collapsed object or frozen star. Wheeler had a gift for language, and black hole stuck immediately. It captured something essential, a region of space from which nothing, no light, no information, no signal of any kind, can escape. But the real question was always whether nature actually makes these things. And the answer came from understanding how stars die. Here's where it gets really beautiful, because it connects to nuclear physics and quantum mechanics in ways that nobody initially expected. A star, any star, is fundamentally a balancing act. You have an enormous amount of mass. The Sun contains about 2 times 10 to the 30th kilograms, which is roughly 330,000 times the mass of the Earth. And all that mass is pulling inward under its own gravity. If gravity were the only thing acting, the star would collapse in minutes. What holds it up is the energy generated by nuclear fusion in its core. Hydrogen atoms are being smashed together at temperatures of about 15 million degrees Celsius to form helium, and in the process, a tiny fraction of the mass is converted to energy according to Einstein's own equation, E equals mc squared. That energy creates outward pressure, radiation pressure, and thermal pressure that exactly balances the inward pull of gravity. The star is in equilibrium. It's a controlled thermonuclear explosion held in check by gravity, sustained for billions of years. But the fuel doesn't last forever. And what happens when it runs out depends entirely on how massive the star is. This is one of those places where a single number, the mass of the star, determines everything about its fate. For a star like the Sun, when the hydrogen in the core is exhausted, the core contracts and heats up enough to start fusing helium into carbon and oxygen. Eventually, the outer layers drift away as a beautiful glowing shell called a planetary nebula, which, by the way, has nothing to do with planets. The name is a historical accident from William Herschel, who thought they looked like planetary disks through his telescope. What's left behind is the core, a dense ball of carbon and oxygen about the size of the Earth, but with roughly the mass of the Sun. A teaspoon of it would weigh several tons. This is a white dwarf, and it's held up not by fusion. There's no more fusion happening, but by a quantum mechanical effect called electron degeneracy pressure. This is where the Pauli exclusion principle, one of the fundamental rules of quantum mechanics, enters astrophysics. Electrons are fermions, which means no two electrons can occupy the same quantum state. When you compress matter to white dwarf densities, the electrons are squeezed so close together that they essentially resist further compression because there are no available quantum states for them to be pushed into. It's a quantum mechanical wall, and it holds the star up. But in 1930, a 19-year-old Indian physicist named Subramanian Chandrasekhar, on a ship sailing from Bombay to Cambridge to begin his graduate studies, worked out something remarkable. He combined special relativity with quantum mechanics and showed that electron degeneracy pressure has a limit. If the mass of the white dwarf exceeds about 1.4 times the mass of the Sun, the electrons would need to move faster than the speed of light to provide enough pressure to hold the star up. And since nothing can move faster than light, the pressure fails. The star cannot be a stable white dwarf. It must collapse further. This mass limit, 1.4 solar masses, is now called the Chandrasekhar limit, and it's one of the most important numbers in astrophysics. Now, Chandrasekhar presented this result to the Royal Astronomical Society in 1935, and the most famous astrophysicist of the era, Sir Arthur Eddington, the very same Eddington who had confirmed Einstein's light-bending prediction in 1919, publicly ridiculed him. Eddington stood up after Chandrasekhar's talk and essentially said the result was absurd, that nature would not allow stars to behave this way. He didn't have a specific physical argument against it. He just found the conclusion aesthetically unacceptable. And because Eddington was Eddington, a towering figure, enormously respected, his dismissal effectively stalled the field for years. Chandrasekhar was devastated. He eventually moved to the University of Chicago, shifted his research to other areas, and didn't receive the Nobel Prize for this work until 1983, nearly 50 years later. It's one of the more painful stories in the history of science, A young genius with the right answer, crushed by the authority of an older scientist who happened to be wrong. But Chandrasekhar was right, and his limit raised an immediate question. What happens to a stellar core that exceeds 1.4 solar masses? The answer is that the electrons get crushed into the protons, forming neutrons through a process called inverse beta decay, and you get a neutron star, an object maybe 20 kilometers across, the size of a city, but containing more mass than the Sun. Now the star is held up by neutron degeneracy pressure, the same quantum mechanical principle but applied to neutrons instead of electrons. And a neutron star is an astonishing thing. The density is about 1 billion tons per teaspoon. The surface gravity is about 200 billion times Earth's gravity. If you dropped a marshmallow onto a neutron star from a height of 1 meter, it would hit the surface with the energy of a small nuclear weapon. But here's the thing. Neutron degeneracy pressure also has a limit. There's a maximum mass for neutron stars too, called the Tolman-Oppenheimer-Volkoff limit, worked out in 1939 by Robert Oppenheimer. Yes, the same Oppenheimer who would later lead the Manhattan Project, along with George Volkoff. That limit is somewhere around 2 to 3 solar masses, though the exact value depends on the details of nuclear physics at extreme densities, which we still don't fully understand. But above that limit, no known force in physics can halt the collapse. Gravity wins completely. The matter falls inward, the curvature of space-time steepens without bound, and you get a black hole. The event horizon forms, and at the center, the equations of general relativity predict that the density becomes infinite, a point of infinite curvature called a singularity. Now that word, singularity, is one of those places where the physics is telling us something important, but we're not entirely sure what. When your equations give you infinity as an answer, it usually means your theory has reached its breaking point. It's not that there's literally a point of infinite density sitting there. It's that general relativity, magnificent as it is probably not the complete story. At those extreme conditions, unimaginable density, subatomic scales, you'd need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity, and we don't have one yet. That's one of the great unsolved problems in physics, and we'll come back to it. But the event horizon itself, the boundary of no return, that part physicists are quite confident about. And starting in the 1960s and 70s, the evidence that black holes actually exist in nature started coming in from some really unexpected directions. And the story of how we went from theoretical curiosity to actual observed objects is one of those great detective stories in science, because nobody set out to find black holes. They stumbled into the evidence sideways, and then spent years arguing about what it meant. Let's start with a discovery that, at first, seemed to have nothing to do with black holes at all. In 1963, a Dutch-American astronomer named Martin Schmidt was studying a strange object called 3C273. It had been catalogued as a radio source, one of many bright points in the sky that emitted strong radio waves. But when Schmidt looked at its optical spectrum, the pattern of light it emitted, nothing made sense. The spectral lines were shifted so dramatically toward the red end of the spectrum that at first he thought there must be an error. But there wasn't. The redshift was enormous, which meant this object was incredibly far away, billions of light years. And here's the problem. If something is that far away and still appears that bright in our telescopes, it has to be producing an almost incomprehensible amount of energy. We're talking about luminosities hundreds of times greater than an entire galaxy. An entire galaxy, with its hundreds of billions of stars, outshone by what appeared to be a single point of light. They called these objects quasi-stellar radio sources, which got shortened to quasars. And for a while, nobody could figure out what could possibly power them. What engine could produce that much energy from such a compact region? The answer, when it finally came together over the next decade or so, was accretion onto a supermassive black hole. Not a black hole formed from a single collapsed star, but something far larger, millions or even billions of times the mass of our sun, sitting at the center of a distant galaxy. Matter falling toward that black hole doesn't just drop straight in. It spirals inward, forming a swirling disk of gas and dust called an accretion disk. And as that material spirals closer and closer to the event horizon, it gets compressed and heated to extraordinary temperatures, tens of millions of degrees. At those temperatures, the disk radiates across the electromagnetic spectrum, from radio waves to visible light to X-rays, and the process is remarkably efficient. Accretion onto a black hole can convert something like 10% of the rest mass energy of the infalling matter into radiation. Think about that for a second. Nuclear fusion in stars, which is already incredibly powerful, converts less than 1% of rest mass into energy. Black hole accretion is roughly 10 times more efficient. That's why quasars can outshine entire galaxies. They've got the most efficient energy source in the known universe. Now, the idea that supermassive black holes might lurk at the centers of galaxies was radical in the 1960s, but the evidence kept piling up. And it wasn't just quasars. Closer to home, astronomers started finding galaxies with unusually active cores, bright, energetic nuclei that didn't behave like normal collections of stars. These became known as active galactic nuclei, and they seemed to exist on a spectrum. Quasars were the most extreme version, blazing away in the distant early universe. But milder versions existed in galaxies much closer to us. The common thread, the unifying explanation that gradually emerged, was a central supermassive black hole with varying amounts of material falling into it. A well-fed black hole with lots of gas spiraling in produces a brilliant quasar. A black hole that's mostly run out of nearby material to consume sits relatively quiet, like the one at the center of our own Milky Way. And yes, our galaxy has one. It's called Sagittarius A star, and it's about 4 million times the mass of the Sun. We know this because of decades of painstaking work, particularly by two teams, one led by Andrea Ghez at UCLA and another by Reinhard Genzel at the Max Planck Institute in Germany. Starting in the 1990s, they tracked individual stars orbiting the galactic center using adaptive optics, a technology that corrects for the blurring of Earth's atmosphere in real time. And what they found was stunning. There are stars at the center of our galaxy, whipping around an invisible point at thousands of kilometers per second, completing full orbits in as little as 16 years. One star, called S2, has been tracked through its entire elliptical orbit. And when you apply Kepler's laws, those same laws we talked about earlier, the ones Kepler worked out from Tycho Brahe's planetary data 4 centuries ago, you can calculate the mass of whatever they're orbiting. 4 million solar masses packed into a region smaller than our solar system. There is nothing that could be except a supermassive black hole. Ghez and Genzel shared the Nobel Prize in Physics in 2020 for this work, alongside Roger Penrose, who had done the crucial theoretical work back in the 1960s, proving that black hole formation was a robust prediction of general relativity, not just some mathematical oddity. Penrose's contribution deserves a moment here because it connects to something important. Remember how Einstein himself didn't believe black holes were real? He thought the singularity was a mathematical artifact, something that wouldn't actually occur in nature. For decades, there was a nagging question. Maybe black holes only form in perfectly symmetrical situations. In the real universe, where nothing is perfectly round or perfectly uniform, maybe the collapse would always avoid creating a true singularity. Maybe the matter would bounce, or swirl, or find some way out. Penrose demolished that argument in 1965 with a brilliant mathematical proof, his singularity theorem. He showed that once enough mass is compressed within a certain region, once a trapped surface forms where all light paths point inward, the formation of a singularity is inevitable regardless of symmetry. It doesn't matter if the collapsing star is lumpy or spinning or irregular. General relativity guarantees the endpoint. That was a watershed moment. It meant black holes weren't a quirk of idealized calculations. They were a prediction that the universe had to honor. But let's come back to the observational side, because there's another thread from the 1960s and 70s that's equally important. And it involves a kind of astronomy that was brand new at the time. X-ray astronomy. You can't do X-ray astronomy from the ground because Earth's atmosphere absorbs X-rays, which is very good news for us biologically, but frustrating if you want to study the high-energy universe. So you need to get above the atmosphere. In 1962, a team led by Riccardo Giacconi launched a small detector on a sounding rocket, basically a brief suborbital flight, and discovered the first X-ray source outside our solar system in the constellation Scorpius. It was called Scorpius X1, and it was astonishingly bright in X-rays. Giacconi would eventually win the Nobel Prize for pioneering X-ray astronomy, and the field exploded through the late 1960s and 70s as satellites like Uhuru, launched in 1970, began systematically mapping the X-ray sky. Here's why this matters for black holes. Remember that accretion disk we talked about? Gas spiraling into a black hole gets heated to millions of degrees. At those temperatures, it radiates primarily in X-rays. So if you want to find black holes that are actively consuming matter, X-ray telescopes are exactly the tool you need. And one of the most important early discoveries was an X-ray source called Cygnus X1, identified in the constellation Cygnus. By the early 1970s, astronomers had matched the X-ray source to a visible star, a blue supergiant, and found that the star was orbiting something invisible. The orbital dynamics told them the invisible companion had a mass of roughly 15 solar masses. That's well above the Tolman-Oppenheimer-Volkoff limit. It couldn't be a neutron star. It was too massive, and it was emitting X-rays in exactly the pattern you'd expect from an accretion disk around a compact object. The case for it being a black hole was strong, even if some holdouts remained cautious. There's a famous story about Stephen Hawking and Kip Thorne making a bet about Cygnus X1 in 1974. Hawking bet that it was not a black hole, which sounds strange, since Hawking had done so much theoretical work on black holes. But he described it as an insurance policy. If black holes turned out not to exist, at least he'd win the bet and get some consolation. By 1990, the evidence was overwhelming enough that Hawking conceded. Thorne got his prize, a subscription to a certain magazine, the details of which have been the subject of much amusement in physics circles. But Hawking's own theoretical work on black holes, done in the 1970s, opened up something far deeper than any bet. And this is where the story takes one of its most remarkable turns, because Hawking discovered something that nobody expected, something that connected black holes to quantum mechanics and thermodynamics in a way that still puzzles physicists today. He showed that black holes aren't perfectly black, they radiate. To understand how that's possible, you need to think about what quantum mechanics says about empty space. And here's the thing. According to quantum field theory, empty space isn't really empty. The vacuum is a seething, restless place. Pairs of particles and antiparticles are constantly flickering into existence and annihilating each other, appearing and disappearing so quickly that you can't directly observe them under normal circumstances. These are called virtual particle pairs, and they're a consequence of the uncertainty principle. Heisenberg's insight that you can't simultaneously pin down certain pairs of properties with perfect precision. Energy can briefly fluctuate, allowing these ghostly pairs to pop up, as long as they vanish again quickly enough. Now, here's what Hawking realized in 1974. Near the event horizon of a black hole, something extraordinary happens to these virtual pairs. Normally, the particle and antiparticle find each other and annihilate. But right at the edge of a black hole, it's possible for one member of the pair to fall past the event horizon while the other escapes. The escaping particle carries away real energy, and to an observer far away, it looks like the black hole is emitting radiation. This is Hawking radiation. And because the escaping particle carries energy away from the black hole itself loses mass over time. It evaporates. Slowly, extraordinarily slowly, for any black hole of astronomical size. A black hole with the mass of our sun would take something like 10 to the power of 67 years to evaporate, which is so much longer than the current age of the universe that it's effectively forever. But the principle matters enormously because it means black holes have a temperature. They're thermal objects. They obey the laws of thermodynamics. And that connection to thermodynamics had actually been hinted at just before Hawking's discovery by a young physicist named Jacob Bekenstein. In 1972, Bekenstein proposed that black holes have entropy, a measure of hidden information, of disorder, and that this entropy is proportional to the area of the event horizon, not the volume enclosed. That's a strange and deep result. In every other physical system we know of, entropy scales with volume. You double the size of a box of gas, you roughly double the entropy. But for black holes, it's the surface area that matters. This has led to decades of speculation about something called the holographic principle. The idea that all the information about what's inside a three-dimensional region might somehow be encoded on its two-dimensional boundary. It sounds almost mystical, but it emerges from hard mathematics, and it's one of the most active areas of theoretical physics today. Some researchers think it might be a crucial clue to that theory of quantum gravity we mentioned earlier. And here's the deeper puzzle that Hawking's radiation creates, one that has haunted physics for 50 years now. If a black hole evaporates completely, what happens to all the information about everything that ever fell into it? In quantum mechanics, information is supposed to be conserved. You can scramble it, mix it up, make it practically impossible to recover, but it's never truly destroyed. The equations of quantum mechanics are reversible in principle. But if a black hole swallows a book, say, and then evaporates into featureless thermal radiation that carries no specific information about that book, then the information seems to be lost, gone, destroyed. That would violate one of the deepest principles of quantum mechanics. This is the black hole information paradox, and when Hawking first proposed it, he argued that the information was indeed lost, that black holes really did destroy information, and quantum mechanics would need to be modified. Most physicists resisted that conclusion. The debate raged through the 1980s and 90s, drawing in some of the sharpest minds in theoretical physics. In 1997, Hawking and Thorne made another bet, this time against John Preskill of Caltech, wagering that information was truly lost. Hawking eventually conceded that bet too, in 2004, acknowledging that information probably does escape somehow, though the precise mechanism remains one of the deepest unsolved problems in all of physics. And that's where things stand, in a way. This beautiful, maddening tangle where the very large and the very small refuse to speak the same language. But let's sit with that for a moment, because the implications ripple outward into places you might not expect. See, the information paradox isn't just some abstract puzzle that theorists argue about at conferences. It's a symptom of something much bigger, the fact that we have two spectacularly successful theories of physics, general relativity and quantum mechanics, and they flatly contradict each other in exactly the situations where we need them most. General relativity describes gravity beautifully. Quantum mechanics describes particles and forces beautifully. But when you try to write down a quantum theory of gravity, when you try to describe what happens at the center of a black hole, or at the very first instant of the Big Bang, where gravity is intense and everything is subatomic, the math breaks. You get infinities. Not the useful kind of infinities that particle physicists learned to tame in quantum electrodynamics back in the 1940s, but ugly, uncontrollable infinities that make the theory spit out nonsense. This is the quantum gravity problem, and it's been the central unsolved challenge of fundamental physics for the better part of a century. Einstein himself spent his last 30 years searching for a unified theory, working at the Institute for Advanced Study in Princeton, filling notebook after notebook, and he never found it. He died in 1955 with the problem wide open. And here we are, 70 years later, and it's still wide open. Though we've learned an enormous amount about what the answer might look like. The most famous attempt is string theory, and it's worth talking about because it illustrates both the ambition and the frustration of this quest. String theory emerged in the late 1960s and early 1970s, originally as an attempt to explain the strong nuclear force, the force that holds protons and neutrons together inside atomic nuclei. It didn't work very well for that purpose, but a few physicists noticed something remarkable. When you wrote down the equations of these tiny vibrating strings, one of the vibrational modes naturally produced a particle with exactly the properties of the graviton, the hypothetical quantum carrier of gravity. A massless particle with spin 2, which is precisely what you'd need if gravity were a quantum force like the others. This was completely unexpected. The theory wasn't designed to include gravity. Gravity just showed up, uninvited, like a guest at a party who turns out to be exactly the person you've been looking for. John Schwartz at Caltech and Joel Shirk in Paris were among the first to recognize this in 1974, and they proposed reinterpreting string theory not as a theory of nuclear physics, but as a theory of everything, a framework that could unify all the forces, including gravity, at the quantum level. For about a decade, almost nobody paid attention. The idea seemed too exotic, too speculative. The strings would have to be unimaginably tiny, around 10 to the minus 35 meters, the Planck length, far smaller than anything we could ever hope to probe directly. And the math required extra dimensions of space. Not 3, but 9 spatial dimensions. Or 10, if you count time. The extra 6 dimensions would have to be curled up so small we can't see them. But in 1984, something happened that physicists call the first superstring revolution. Schwartz and Michael Green showed that string theory was free of certain mathematical inconsistencies, anomalies, that everyone assumed would kill it. Suddenly, the theory looked viable, and within months, hundreds of physicists pivoted to working on it. Ed Witten at Princeton, widely considered one of the most brilliant mathematical physicists alive, threw his weight behind it and made enormous contributions. By the late 1980s, string theory was the hottest topic in theoretical physics. And then it got complicated. It turned out there wasn't one string theory. There were five different versions, each mathematically consistent, each claiming to be the fundamental theory of nature. That's not great if you're looking for the one true description of reality. But in 1995, Witten proposed that all five string theories were actually different limits of a single deeper theory he called M theory. The M might stand for master, or membrane, or mystery. Witten was deliberately cagey about it. M theory lives in 11 dimensions and includes not just strings, but higher dimensional objects called branes. And here's the thing. Nobody has actually written down M theory. We know some of its properties. We know it must exist because of the mathematical relationships between the five string theories, but the full formulation remains unknown. It's like knowing there's a mountain behind the clouds because you can see its shadow, but you've never actually seen the mountain itself. Now, I should be honest with you about where string theory stands today, because it's genuinely controversial, and the controversy itself tells you something important about how science works at the frontier. String theory has produced extraordinary mathematical insights. It's given us the most concrete version of the holographic principle, something called the ADS/CFT correspondence, proposed by Juan Maldacena in 1997, which showed that a theory of gravity in a particular kind of curved spacetime is mathematically equivalent to a quantum theory without gravity living on the boundary of that spacetime. This was a stunning result, and it's been checked in thousands of calculations. It strongly suggests that the holographic principle is real, that gravity and spacetime might genuinely emerge from more fundamental quantum information on a boundary. But here's the frustration. String theory, at least so far, has made no testable predictions about our specific universe. The extra dimensions can be curled up in an astronomically large number of different ways. Estimates range up to 10 to the 500 different configurations, and each one gives you a different set of particle masses, forces, and constants. This landscape of possibilities is so vast that critics argue the theory can accommodate almost anything, which means it predicts almost nothing. Lee Smolin, a physicist at the Perimeter Institute, has been one of the most vocal critics, arguing that string theory's dominance has crowded out alternative approaches. Peter Woit at Columbia has made similar arguments. The string theorists counter that the mathematical consistency of the theory is itself a powerful constraint, and that we simply haven't understood it well enough yet to extract predictions. And there are alternative approaches. Loop quantum gravity, developed primarily by Lee Smolin, Carlo Rovelli, and Abhay Ashtekar, starting in the late 1980s, takes a completely different tack. Instead of adding new ingredients like strings and extra dimensions, it tries to apply quantum mechanics directly to general relativity's description of space-time itself. The result is a picture where space isn't smooth and continuous at the smallest scales, but is instead woven from discrete chunks, tiny loops of gravitational field that link together into a structure physicists call a spin network. Space, in this picture, is granular. There's a smallest possible volume, roughly the Planck volume, about 10 to the minus 99 cubic centimeters. You literally cannot have a region of space smaller than that. It's not that our measurements aren't precise enough. Space itself comes in minimum-sized pieces. Think about that for a second. We're so used to thinking of space as this perfectly smooth, infinitely divisible backdrop that the idea of it being pixelated, like a screen if you zoom in far enough, feels almost absurd. But loop quantum gravity says that's exactly what happens. And it has at least one tantalizing result. When you apply it to the Big Bang, the singularity that general relativity predicts at the very beginning of the universe gets resolved. Instead of everything being crushed to a point of infinite density, the quantum geometry bounces. The universe contracts to a minimum size and then re-expands. Some researchers call this the Big Bounce. It suggests our Big Bang might have been the rebound from a previous collapsing universe. Neither string theory nor loop quantum gravity has been experimentally confirmed. And that's the honest state of affairs. We're at a point in physics where the questions we're asking: what happens at the Planck scale? What's inside a black hole singularity? What happened at the very first instant of the universe? Involve energies and scales so extreme that we may never be able to probe them directly with particle accelerators. The Large Hadron Collider at CERN, the most powerful accelerator ever built, probes energies about a quadrillion times too low to reach the Planck scale. Building an accelerator that could reach those energies would require a particle collider roughly the size of the Milky Way galaxy. That's not happening. So physicists are looking for indirect evidence. One possibility is gravitational waves, those ripples in space-time that Einstein predicted in 1916, and that were finally detected directly in September 2015 by the LIGO observatories. And that detection, by the way, is one of the great engineering stories of modern science, because it required measuring a change in distance of about 1,000th the diameter of a proton across a 4-kilometer laser beam. 1,000th the diameter of a proton. The precision involved is almost incomprehensible. The mirrors had to be isolated from every conceivable vibration: trucks on nearby highways, ocean waves hitting distant coastlines, even the quantum fluctuations of the laser light itself. The team, led by Kip Thorne, Rainer Weiss, and Barry Barish, worked on the problem for over 4 decades before that first detection, and what they heard was the chirp of 2 black holes, each about 30 times the mass of our Sun, spiraling into each other and merging about 1.3 billion light-years away. The signal matched general relativity's predictions with extraordinary precision. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, black hole mergers, neutron star mergers, and even collisions between a black hole and a neutron star. In August 2017, the merger of 2 neutron stars was detected both in gravitational waves and in light across the electromagnetic spectrum, from gamma rays to radio waves. That single event confirmed that neutron star mergers produce heavy elements like gold and platinum through a process called rapid neutron capture, or the R process. So the gold in any ring you might be wearing was likely forged in the violent collision of 2 dead stars, billions of years ago, before our solar system even formed. The atoms were scattered into space, mixed into the cloud of gas and dust that eventually collapsed to form our sun and planets, and ended up on your finger. That's not poetry. That's nuclear astrophysics confirmed by observation. But gravitational waves might also carry whispers of quantum gravity. If space-time is granular at the Planck scale, as loop quantum gravity suggests, then gravitational waves traveling across billions of light-years might accumulate tiny distortions, a faint blurring or dispersion that could, in principle, be detected with sensitive enough instruments. So far, no such effect has been seen, which puts constraints on some models. Future space-based detectors like LISA, planned for launch in the 2030s, will open up entirely new frequency ranges and might reveal subtler effects. And then there's the cosmic microwave background, that ancient light from when the universe was only about 380,000 years old. We talked earlier about how it tells us about the early universe, but here's what's particularly exciting. If quantum gravitational effects left imprints during the very first fraction of a second after the Big Bang, those imprints might be preserved as subtle patterns in the cosmic microwave background. Specifically, a period called cosmic inflation, a brief, violent expansion of the universe in its first tiny fraction of a second, would have stretched quantum fluctuations to cosmic scales, and those fluctuations seeded the large-scale structure of the universe we see today. The galaxies, the clusters of galaxies, the vast cosmic web of matter, all of it traces back to quantum jitters in the infant universe, amplified by inflation. This is one of those ideas that sounds too wild to be true, but the evidence is remarkably strong. The satellite missions, COBE, WMAP, and most recently, Planck, have mapped the cosmic microwave background with exquisite precision, and the pattern of tiny temperature variations matches the predictions of inflationary theory with stunning accuracy. The universe, at its largest scales, carries the fingerprint of quantum mechanics, and if inflation happened at high enough energies, it might even carry fingerprints of quantum gravity, primordial gravitational waves that would leave a distinctive swirling pattern called B-mode polarization in the microwave background. Detecting that pattern is one of the holy grails of observational cosmology. Several experiments are searching for it right now, from telescopes at the South Pole to balloon-borne instruments flying in the stratosphere. So we're in this remarkable era where the deepest questions in physics, questions about the nature of space and time, about what happens inside black holes, about how the universe began, are being pursued not just with pen and paper, but with actual observations. The tools are gravitational wave detectors, microwave background satellites, X-ray telescopes, and even the Event Horizon Telescope, that planet-spanning network of radio dishes that produced the first image of a black hole's shadow in 2019. The supermassive black hole in the galaxy M87, 6.5 billion times the mass of our Sun, 55 million light-years away. That image, that glowing ring of hot gas around a dark central shadow, looked almost exactly like what general relativity predicted. And in 2022, the same team released an image of Sagittarius A star, the black hole at the center of our own galaxy, the one whose mass was pinned down by tracking those orbiting stars. But what the images can't show you is what's happening beyond the event horizon. And that brings us back to the question that connects everything we've been talking about tonight, the question of what space and time actually are at the deepest level. Because general relativity tells us that space-time is a dynamic thing, shaped by matter and energy, capable of curving, stretching, even tearing at a singularity. And quantum mechanics tells us that everything, at small enough scales, is subject to uncertainty, fluctuation, superposition. Put those two ideas together, and you get the suggestion that space-time itself might be a quantum entity, something that emerges from a deeper layer of reality, the way temperature emerges from the jittering of molecules, the way the smoothness of water emerges from billions of individual atoms bouncing around. And that idea, that space-time is emergent, is one of the most profound shifts in thinking that physics has undergone in the last few decades. So let's sit with it for a while, because it changes how you think about almost everything. Start with something familiar. Think about the surface of a lake on a calm morning. From a distance, it looks perfectly smooth, continuous, like a sheet of glass. You could describe it with simple mathematics. Height of the water at every point, gentle waves rolling across it. But zoom in far enough and that smoothness dissolves. You find individual water molecules bouncing and colliding with gaps between them. The smooth surface was never fundamental. It was a large-scale approximation, a useful description that works beautifully at human scales, but breaks down when you look too closely. Now imagine that space itself, the three-dimensional arena you move through every day, the thing you take for granted as the stage on which physics happens, might be exactly like that lake surface. Smooth and continuous at the scales we can measure, but grainy, fluctuating, maybe even undefined at the Planck scale, down around 10 to the minus 35 meters. That's not just small, that's absurdly, incomprehensibly small. If an atom were blown up to the size of the observable universe, the Planck length would still be smaller than a single atom in that blown-up picture. We are talking about a regime so far beyond our instruments that it might seem pointless to even think about it. But here's the thing. The consequences of space-time being emergent don't stay locked away at the Planck scale. They ripple upward. They affect how we think about black holes, about the Big Bang, about the information paradox, about the very meaning of geometry. One of the people who's pushed this idea furthest is Mark van Ramsdonk, a theoretical physicist at the University of British Columbia. In 2010, he wrote a paper with a title that sounds almost poetic, Building Up Space-Time with Quantum Entanglement. The core idea is striking, he argued, building on Maldaceno's ADS/CFT correspondence, that the connectivity of space-time, the fact that 2 points in space are near each other rather than far apart, is related to quantum entanglement between the underlying degrees of freedom. If you take two regions that are entangled and gradually reduce their entanglement, the space-time between them stretches and eventually pinches off, like pulling taffy until it snaps. Entanglement, in this picture, is the glue that holds space together. Remove the entanglement, and space itself falls apart. Now, that's a wild claim. Let's unpack it a little. Quantum entanglement, you'll recall, is that strange correlation between particles where measuring one instantly tells you something about the other, no matter how far apart they are. Einstein famously called it spooky action at a distance, and was deeply uncomfortable with it. But experiment after experiment has confirmed that entanglement is real. It's one of the most well-tested features of quantum mechanics. What van Ramsdonk and others are suggesting is that this same phenomenon, entanglement, isn't just a quirky feature of quantum particles. It might be the fundamental fabric from which space emerges. The geometry of the universe, distances, angles, curvature, all of it, might be a macroscopic manifestation of an underlying web of quantum entanglement. This connects beautifully to something we touched on earlier, the holographic principle. Remember that idea from Bekenstein and 't Hooft and Susskind, that the information content of a region of space scales not with its volume, but with its surface area. In the emergent space-time picture, that starts to make sense in a new way. If space-time is built from entanglement, then the amount of space-time you can construct is limited by the amount of entanglement available, and entanglement between a region and its surroundings naturally scales with the boundary area. The holographic principle stops being a mysterious coincidence and starts looking like a natural consequence of how space-time is stitched together. And here's where it gets really interesting for the information paradox. Remember the problem. A black hole forms, swallows information, then evaporates via Hawking radiation that appears to carry no information about what fell in. Information seems to be destroyed, violating a sacred principle of quantum mechanics. Well, if space-time is emergent, if the interior of a black hole is connected to the exterior through subtle patterns of entanglement, then maybe the information isn't lost at all. Maybe it's encoded in the entanglement structure itself, gradually released as the black hole evaporates, in ways that are incredibly scrambled but technically recoverable. In 2013, Juan Maldacena and Leonard Susskind proposed something remarkable, the ER equals EPR conjecture. ER refers to Einstein-Rosen bridges, which are wormholes, those hypothetical tunnels through space-time that Einstein and Nathan Rosen described back in 1935. EPR refers to the Einstein-Podolsky-Rosen paradox, which is the original paper about quantum entanglement, also from 1935. Maldacena and Susskind suggested that these two things, wormholes and entanglement, are actually the same phenomenon seen from different angles. Every pair of entangled particles is connected by a tiny, non-traversable wormhole, and every wormhole is a manifestation of entanglement. Think about what that means. Two particles on opposite sides of the universe, entangled with each other, are connected by a thread of space-time so thin and so quantum mechanical that you could never send a message through it, but it's there. And the space-time we experience, the smooth three-dimensional space we walk through, is woven from trillions upon trillions of these threads. It's like a fabric where every thread is an entanglement connection, and the overall pattern of the weave determines the geometry. What's close to what, where space curves, how distances work. Now I want to be honest with you. This is frontier physics. None of this is settled. The ER equals EPR conjecture is a conjecture. It hasn't been proven, and there are physicists who are skeptical. The emergent space-time program is still being developed, and there are deep technical challenges. For one thing, most of the concrete results come from the ADS/CFT correspondence, which works in anti-d Sitter space, a universe with a negative cosmological constant. Our universe has a positive cosmological constant. It's expanding, accelerating. So there's a real question about whether these beautiful results in ADS space translate to the universe we actually live in. That's one of the biggest open problems in the field. But even with those caveats, the direction of travel is remarkable. A generation ago, most physicists thought of space-time as fundamental, as the stage on which quantum fields dance. Now a growing number of researchers think the stage itself is part of the performance. Space-time isn't the container. It's the thing that needs to be explained. And this shift has practical consequences for how people approach quantum gravity. If you're trying to quantize gravity the old-fashioned way, treating the gravitational field as just another quantum field living on a fixed background space-time, you run into those terrible infinities we talked about. But if space-time itself is emergent, then maybe you shouldn't be trying to quantize it directly. Maybe you should be looking for the underlying quantum system from which space-time emerges, and gravity would come along for free. That's essentially the philosophy behind the ADS/CFT approach. The boundary theory, the conformal field theory, has no gravity in it at all. It's just a regular quantum theory living on a fixed, lower-dimensional space. But somehow, through the magic of the correspondence, it encodes a higher-dimensional universe with gravity, black holes, gravitational waves, the whole package. Gravity isn't put in by hand. It emerges. There's something deeply satisfying about that, even if we don't fully understand it yet. It suggests that gravity, the first force humans ever noticed, the one that makes apples fall and planets orbit, the one Newton wrote down in 1687 and Einstein reimagined in 1915, might be the last force we truly understand, because understanding it requires understanding the origin of space-time itself. And that brings us to cosmology, to the biggest questions of all. Because if space-time is emergent, what does that say about the Big Bang? The traditional picture has the universe beginning as a singularity, a point of infinite density and curvature where general relativity breaks down. But if space-time itself only emerges at scales larger than the Planck length, then the concept of a point might not even make sense at the very beginning. There might not have been a singularity at all. There might have been something else, something that our current language and mathematics can barely describe. The loop quantum gravity folks, as we mentioned, get a big bounce instead of a big bang. A previous contracting universe that reached a maximum density and then re-expanded. In string cosmology, there are models where the Big Bang is the collision of higher dimensional membranes. In the emergent spacetime picture, the beginning of the universe might be the moment when entanglement first organized itself into something recognizable as geometry. We don't know which of these pictures, if any, is correct. But here's what's beautiful about where we are right now. We're not just speculating in the dark. We have observational programs, gravitational wave detectors, microwave background experiments, black hole imaging, that are pushing into regimes where these ideas might leave detectable signatures. The next generation of gravitational wave detectors, like the Einstein telescope planned for Europe or Cosmic Explorer in the United States, will be sensitive enough to probe the physics of neutron star interiors and the ringdown of merging black holes with extraordinary precision. Any deviation from general relativity's predictions in those signals could be a clue. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the mid-2030s, will open up an entirely new frequency band of gravitational waves, catching signals from supermassive black hole mergers across the observable universe, from thousands of compact binary systems in our own galaxy, and possibly from exotic sources we haven't even predicted yet. And then there's the cosmic microwave background. We talked about the search for B-mode polarization, that signature of primordial gravitational waves from inflation. But the microwave background contains other information too. Its temperature fluctuations, mapped with extraordinary precision by the Planck satellite, already tell us the universe is spatially flat to within about 0.5%. They tell us the age of the universe, 13.8 billion years. They tell us the relative amounts of ordinary matter, and dark energy. And future experiments might detect even subtler patterns, non-Gaussianities in the fluctuations, for instance, which could distinguish between different models of inflation or even reveal signs of a pre-Big Bang epoch. So we're living in this extraordinary moment where the oldest questions humanity has ever asked. What is the universe made of? How did it begin? What is space? What is time? Are being addressed with real instruments and real data. Not definitively answered, not yet, maybe not for a long time, but genuinely pursued. And the answers, when they come, will almost certainly be stranger than anything we've imagined so far. Because every time we've peeled back a layer, from the Babylonians tracking planets to Kepler finding ellipses to Newton, discovering gravity to Einstein, reimagining it as geometry to Hawking showing that black holes radiate. Every single time, the universe has turned out to be weirder, more subtle, more interconnected than the previous generation thought possible. There's one more piece of this puzzle that we haven't really talked about yet, and it's the one that makes up most of the universe. I'm talking about the dark sector, dark matter and dark energy. Because here's a fact that should stop you in your tracks if you really let it sink in. Everything we've discussed tonight, all the stars, all the galaxies, all the black holes, all the gas and dust and planets and people, all of that makes up roughly 5% of the total energy content of the universe. 5%. The rest is dark. Dark matter, making up about 27%, and dark energy, making up about 68%. Together, roughly 95% of everything that exists is stuff we have never directly detected, never held in a laboratory, never fully explained. We know it's there. We're quite confident about that, but we don't know what it is. And that's not a small gap in our understanding. That's almost the entire universe sitting in a category labeled unknown. Let's start with dark matter, because it has the longer history, and honestly, it's one of the best detective stories in all of science. The year is 1933, and we're at the California Institute of Technology, where a Swiss astronomer named Fritz Zwicky is doing something that sounds straightforward, but turns out to be revolutionary. He's studying the Coma Cluster, a massive collection of over 1,000 galaxies about 320 million light-years away. And Zwicky does a clever thing. He measures how fast the individual galaxies in the cluster are moving relative to each other. He uses the Doppler shift of their light, the same basic principle behind why an ambulance siren changes pitch as it passes you. If a galaxy is moving toward us, its light gets slightly bluer. If it's moving away, slightly redder. From those shifts, you can calculate speeds. So Zwicky measures all these speeds, and then he does a calculation. He uses the virial theorem, a result from classical mechanics that relates the average kinetic energy of a system to its gravitational potential energy. Basically, if you know how fast things are moving in a gravitationally bound system, you can work backward to figure out how much mass must be present to keep the system from flying apart. Makes sense, right? The faster things are moving, the more gravity you need to hold them together, which means more mass. And here's where it gets strange. When Zwicky runs the numbers, the galaxies in the Coma Cluster are moving way too fast. Like, dramatically too fast. Given the amount of visible matter he can see, all the glowing stars and gas, there's nowhere near enough gravitational pull to keep those galaxies bound together. The cluster should have flown apart long ago. He calculates that there must be about 400 times more mass than what's visible. He calls it Dunkelmaterie, dark matter. And then, for the most part, the physics community shrugs and moves on. Zwicky, you should know, was a brilliant and notoriously difficult person. He called his colleagues at Caltech spherical bastards. Because, he said, they were bastards no matter which way you looked at them. He was abrasive, combative, and often right about things decades before anyone else caught up. Dark matter was one of those things. It took about 40 years for the idea to come roaring back, and the person most responsible was Vera Rubin. Working with Kent Ford at the Carnegie Institution in Washington through the 1960s and 1970s, Rubin measured the rotation curves of spiral galaxies. That is, how fast stars orbit at different distances from the galactic center. Now, you'd expect something very specific here, based on everything Newton taught us. In our solar system, Mercury orbits the Sun much faster than Neptune, because most of the mass is concentrated in the center, and gravity weakens with distance. So you'd expect the same pattern in a galaxy. Stars near the center orbiting fast, stars at the edges orbiting much slower. But that's not what Rubin found. Not at all. Galaxy after galaxy, the rotation curves came out flat. Stars at the outer edges of galaxies were orbiting just as fast as stars much closer to the center. This makes no sense if the only mass present is the visible stuff, the stars and gas you can see. There has to be an enormous amount of additional mass extending far beyond the visible disk of the galaxy, forming a kind of invisible halo. And it has to be mass that doesn't emit light, doesn't absorb light, doesn't interact with light at all. Dark matter. This is one of those results that's so clean, so repeatable, and so impossible to explain away that it changed the field permanently. Rubin measured it in dozens of galaxies. Other astronomers confirmed it in hundreds more. The pattern is universal. Every large galaxy we've ever studied has a rotation curve that demands dark matter, and the amount is always roughly the same ratio, about 5 to 6 times more dark matter than ordinary matter. Now, you might be thinking, couldn't there just be a lot of dim ordinary matter out there, failed stars, rogue planets, black holes, cold gas clouds, stuff that's made of regular atoms but just doesn't glow. Astronomers thought of that too, and they have a name for such objects. MACHOs, massive astrophysical compact halo objects, and people looked for them through gravitational microlensing surveys in the 1990s, watching for the brief brightening of background stars when a massive dark object passes in front of them. Astronomers established that MACHOs can account for at most a small fraction of the missing mass, not nearly enough. There's another argument, and it's even more powerful. It comes from Big Bang nucleosynthesis, the process by which the lightest elements were forged in the first few minutes after the Big Bang. The relative abundances of hydrogen, deuterium, helium, and lithium that we observe in the universe depend very sensitively on the total density of ordinary baryonic matter, protons and neutrons, and those observed abundances match the predictions beautifully, but only if ordinary matter makes up about 5% of the total energy density, not 27%, not 32%. 5. So whatever dark matter is, it's not made of protons and neutrons. It's not atoms. It's something else entirely. The leading candidates for decades have been WIMPs, weakly interacting massive particles. The idea is elegant. If there exists a new type of subatomic particle that has mass, feels gravity, but interacts with ordinary matter only through the weak nuclear force, one of the four fundamental forces, the same one responsible for certain types of radioactive decay, then such particles would have been produced abundantly in the early universe. And here's what's really clever. When you calculate how many WIMPs would survive to the present day, given the expansion rate of the universe and the rate at which they'd annihilate each other, you get a density that's remarkably close to the observed density of dark matter. This coincidence is called the WIMP miracle, and it got a lot of physicists very excited. So people built detectors deep underground to shield them from cosmic rays. Experiments like Xenon in Italy, LUX and its successor, LZ in South Dakota, Pandax in China. These are massive tanks of ultra-pure liquid xenon, surrounded by the most sensitive light detectors ever built, waiting for the faintest flash that would signal a dark matter particle bumping into a xenon nucleus. They've been running for years, and they've found nothing, not one confirmed detection. The limits have gotten tighter and tighter, ruling out more and more of the parameter space where WIMPs could hide. It's not impossible that WIMPs exist, there's still room, but the miracle is looking less miraculous. Other candidates are on the table. Axions, originally proposed in the late 1970s to solve a different problem in particle physics, why the strong nuclear force respects a certain symmetry it has no obvious reason to respect. Axions would be extraordinarily light, perhaps a billionth the mass of an electron or less, but they could be produced in enormous quantities and collectively act as dark matter. Experiments like ADMX are searching for them using the idea that in a strong magnetic field, an axion might convert into a detectable photon. It's a beautiful experiment, incredibly sensitive, and so far also no detection. But the search space is vast. There are even more exotic possibilities. Sterile neutrinos, primordial black holes, not the stellar mass kind we talked about earlier, but tiny ones formed from density fluctuations in the very early universe. Some theorists have proposed modifying gravity itself rather than invoking new particles. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgrom in 1983, changes Newton's second law at very low accelerations and can reproduce galaxy rotation curves remarkably well without any dark matter at all. But MOND struggles with galaxy clusters, with the cosmic microwave background, with gravitational lensing observations, particularly the bullet cluster, where two galaxy clusters collided, and the gravitational lensing map clearly shows the mass separated from the visible gas, exactly as you'd expect if dark matter is a real substance that passed through the collision while the gas got stuck. That observation, from 2006, is one of the strongest single pieces of evidence that dark matter is a thing, not just a modification of physics. So dark matter remains a mystery. We know how much there is. We know how it's distributed. We can map it through gravitational lensing. We can simulate its behavior in cosmological computer models, and those simulations reproduce the large-scale structure of the universe, the cosmic web of filaments and voids, with stunning accuracy. But we don't know what particle it is. We've never caught one, and that's humbling. Now let's talk about the other piece of the dark sector, and honestly, this one is even stranger: dark energy. In 1998, two independent teams of astronomers, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were both trying to measure how the expansion of the universe is slowing down, because that's what everyone expected. The universe is full of matter. Matter has gravity. Gravity pulls things together. So the expansion that started with the Big Bang should be gradually decelerating. The question was just, by how much? They used Type 1a supernovae as standard candles. These are a particular type of stellar explosion that occurs when a white dwarf accumulates enough matter to reach a critical mass, about 1.4 solar masses, the Chandrasekhar limit. Because they all explode at roughly the same mass, they all have roughly the same intrinsic brightness. So if you measure how bright one appears from Earth, you can calculate how far away it is. And if you measure its redshift, you know how fast it's receding. Plot distance against recession speed for dozens of these supernovae, and you can trace the expansion history of the universe. Both teams expected to find deceleration. Both teams found the opposite. The expansion of the universe is accelerating. Distant supernovae were dimmer than they should have been, farther away than a decelerating universe would predict. Something is pushing the universe apart, and it's winning against gravity on the largest scales. That something got the name dark energy, and Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize for the discovery. Here's what's wild about dark energy. The simplest explanation is Einstein's cosmological constant, the very term he added to his field equations in 1917 to keep the universe static, and then supposedly called his greatest blunder when Hubble showed the universe was expanding. Turns out, maybe it wasn't a blunder at all. The cosmological constant represents a constant energy density inherent to space itself. Every cubic meter of empty space has a tiny amount of energy, and as space expands, you get more space, which means more energy, which drives more expansion. It's a runaway process. And the value is absurdly small. The energy density of dark energy is roughly equivalent to about 6 protons per cubic meter. That's almost nothing. But space is very, very big, and that tiny density adds up across billions of light years to become the dominant component of the universe. Now here's the problem. If you try to calculate the energy of empty space using quantum field theory, adding up the zero-point energies of all the quantum fields, you get a number that is roughly 10 to the power of 120 times larger than the observed value. That's not a small discrepancy. That's been called the worst prediction in the history of physics. Something is either deeply wrong with our understanding of quantum field theory, or there's a cancellation mechanism we haven't discovered, or the cosmological constant isn't what we think it is. Some physicists have proposed that dark energy isn't constant at all, that it's a dynamic field, sometimes called quintessence, that changes over time. If that's the case, the fate of the universe depends on how it evolves. With a cosmological constant, the universe expands forever, and galaxies beyond our local group eventually recede so fast that their light can never reach us. The observable universe slowly empties out and cools toward heat death. With quintessence, other scenarios become possible, including, in some models, a big rip, where the expansion accelerates so violently that it eventually tears apart galaxies, then solar systems, then atoms themselves. Recent observations have added intrigue. Data from the Dark Energy Spectroscopic Instrument, DESI, released in 2024, hints that dark energy might indeed be changing over time, though the evidence is still preliminary. If confirmed, it would be one of the most significant cosmological discoveries since the accelerating expansion itself. So here we are. 95% of the universe is dark, invisible, untouchable, unexplained. And yet, through centuries of patient observation, brilliant reasoning, and sometimes sheer stubbornness, we've mapped its effects with extraordinary precision. We know the shape of what we don't understand, and I think that's actually a beautiful place to end up tonight. Because the story we've traced, from Babylonian astronomers recording the wandering of planets on clay tablets, through Kepler's laws and Newton's gravity and Einstein's curved space-time, through black holes and Hawking radiation and entangled particles that might weave the fabric of space itself. That story has a consistent theme. Every generation thought they were close to a complete picture, and every generation discovered that the universe was deeper, stranger, and more magnificent than they'd imagined. You're lying here, maybe drifting, maybe still following along, and the same sky that puzzled those Babylonian scribes is above you right now. The same gravity that Newton described is holding you gently against your bed. The same space-time that Einstein reimagined is ticking away your seconds and curving around the Earth beneath you. The same dark matter is holding your galaxy together as it rotates, and the same dark energy is quietly stretching the space between galaxy clusters while you breathe. You don't need to understand all of it. Nobody does. Not yet. The universe is patient. It's been here for 13.8 billion years, and it's not going anywhere. The questions will still be there in the morning. The stars will still be burning. The dark matter will still be holding things together in ways we can't quite see. And somewhere, right now, someone is sitting in front of a computer screen or peering at data from a detector buried deep underground, or adjusting a telescope on a mountaintop, and they're about to notice something that doesn't quite fit, something that will open the next door. That's how it's always worked. That's how it will keep working. And for now, that's enough. The universe is vast and dark and strange, and you are part of it, a small arrangement of atoms that somehow learned to wonder about the rest. Let that be the last thought you carry into sleep. You are the universe, looking back at itself, asking what it's made of, and slowly, beautifully, finding out.